Today I'll be introducing our JGR paper titled The PLUM Earthquake Early Warning Algorithm, a retrospective case study of West Coast USA data. This was a collaborative effort that would not have been possible without the co-authors listed here. In general, earthquake early warning can be described in 5 primary steps. The earthquake starts, telemetry station to data center, earthquake detection, alert region derived, and finally alert dissemination. Of these 5 steps, the paper I'm describing today only investigates the first 3 topics through earthquake detection. This paper does not discuss alert methods, alert regions, and alert success methods. We use the PLUM algorithm, which stands for Propagation of Local Undamped Motion, initially designed and refined by Hoshiba and Kodera. PLUM is a ground motion-based algorithm. It is not designed to report earthquake magnitude or location. The method is extremely simple. Identify large ground motions and issue a detection. It is as simple as it gets. Ground motion detections are based on ground intensity estimates using the modified Mercalli intensity metric MMI. For each station, PLUM ingests 1-second data packets and generates MMI grams as shown here. Triggering thresholds are predefined. In this example, the threshold is set to 4. A trigger would be issued for the MMI gram on the left, but not for the MMI gram on the right. As you can see, different threshold levels will net different results. We find a 2-station method outperformed a 1-station method. In the 2-station method, the initial trigger must be confirmed by a trigger on a neighboring station. Our retrospective test showed that all investigated 2-station methods removed all false alerts. Our aim is to detect magnitude 5 and above earthquakes. To do so, we prefer MMI thresholds of 4 and 3 for the first and second thresholds, respectively. These values reduce the detection of smaller magnitude quakes. We test 2 different data sets, a 6-year data set from 2012 to 2018, shown on the left, and a test suite of known problematic data, shown on the right. The purple stars, both big and small, highlight earthquakes that PLUM detected. As you can see, most of the PLUM detected events are onshore. However, PLUM did detect some offshore earthquakes, including 2 offshore quakes that were problematic for other algorithms. The brown stars on this map are the most problematic, showing large events that PLUM did not detect. Notably, these missed events are mostly offshore or at the edge of the network. For the 6-year dataset, PLUM detected 79 earthquakes. Within this dataset, there are 20 magnitude 5+ earthquakes, of which PLUM detected 10. But as we will subsequently see, PLUM did detect all 5+ earthquakes that are theoretically detectable. The PLUM latencies, time of detection after origin time, are 8 and 6 seconds for the mean and median, respectively, values on par with other algorithms. The most notable finding for the test suite data is that PLUM successfully avoids all teleseismic signals, calibration pulses, and anomalous signals, and no false detections were issued for either dataset. We next compare what PLUM detected with what is theoretically detectable. Events below the dashed or solid lines are not theoretically detectable. For both datasets, for the larger magnitude 5 and plus events, PLUM is detecting everything that is theoretically detectable. As the seismic network continues to expand, these theoretical detection limits will become lower, allowing PLUM to theoretically be able to detect more events. The take-home: PLUM detects offshore events that produce at least moderate onshore ground motions, including an event problematic for other algorithms. PLUM's detection times are as timely and sometimes faster than other earthquake early warning detection times. PLUM correctly avoids erroneous detections for any teleseismic calibration pulses and anomalous signals in the test suite. Results presented here are conservative. We expect PLUM to perform better using ShakeAlert real-time data, which contains approximately double the number of stations used in this work.